Next, we're going to look at the shell method, which is another way of calculating the volume for a solid of revolution. Here, the volume of the solid S is going to be divided into a bunch of concentric cylindrical shells. For the previous method, the disk method, the solid was sliced up like a loaf of bread, but this time with the shell method, the solid is more like the rings of a tree or the layers of an onion. If you look at the picture of the planar region, when we use the shell method, a representative rectangle will be parallel to the axis of rotation. So that's a difference between the shell and the disk method. In the shell method, the representative rectangle is parallel to the axis of rotation, so it sweeps out a thin cylindrical shell. And each shell will have a volume 2 pi times the shell radius times the shell height times the small width of the shell, which is dx. So the total volume of the solid is going to be the definite integral from a to b, 2 pi radius times height with respect to x. Here both the shell radius and shell height are functions of x. For a horizontal rotation axis, the integral will be with respect to y. You can see in the picture on the left for the planar region, since we're rotating around the horizontal axis and the representative rectangle is parallel to the axis of rotation, then it has a tiny width dy, so the integral will be with respect to y. And then each small shell will have volume dv, which is 2 pi the shell radius as a function of y, times the shell height as a function of y, times the small width dy. So the total volume will be the definite integral from a to b, 2 pi shell radius shell height with respect to y. Just to note, by unrolling a cylindrical shell into a rectangular slab, like in this picture, then we can see that the length of the slab will be the circumference of the cylinder, 2 pi p. The height of the slab will be the height of the cylindrical shell. The width of the slab will be the width of the cylindrical shell, dx. So it's easy to remember that the small volume or differential volume will be the length times the height times the small width. In this example, find the volume of the solid obtained by revolving the region bounded by y is equal to square root x, the x-axis, and the line x is equal to 4 around the y-axis. First, you can make a sketch of the region. Since we're using shells and we're rotating around the y-axis, the representative rectangle will be parallel to the y-axis, and it has a small width dx, so our integral will be with respect to x. So the height of the rectangle will be just root x, or root x minus 0, and the radius of the shell is the distance from the axis of rotation to the rectangle. So that can be x minus 0 or just x. And you can see the integral will go from x is equal to 0 to x is equal to 4. So it will be 0 to 4, 2 pi, radius times height with respect to x. So x to the power 1 times x to the half will be x to the 3 over 2, as we add the powers. So now we can take the antiderivative for x to the 3 over 2. It will be x to the 3 over 2 plus 1 is 5 over 2, divided by 5 over 2, or multiplied by 2 over 5, from 0 to 4. When we plug in the upper limit 4, it's square rooted into power 5. So square root 4 is 2, and 2 to the power 5 is 32. And at the lower limit, it will be 0. So just check if you get 128 pi over 5 units cubed. And again, the graph of the actual solid is just given for reference. It has a shape similar to an arena or stadium. In the next example, find the volume of the solid obtained by revolving the region from the previous example E around the x-axis. So it's the same region as the previous example, except now we're revolving around the x-axis and we're using shells. So the representative rectangle will be parallel to the x-axis. You can see it has a small width dy, so the integral will be with respect to y. So if y is equal to root x, if you square both sides, x will be equal to y squared. So the function in terms of y is y squared. So we can look at the height of the rectangle. So instead of the height being upper minus lower, now from the picture you can see it will be right minus left. So the height of the rectangle will be 4 minus, and instead of the function root x, it's a function of y, so it will be y squared. The radius of the shell is the distance from the axis of rotation to the rectangle. So here we can see it will just be y, or y minus 0. And remember that we're integrating with respect to y, so the integral will go from 0 to 2. Integral from 0 to 2, 2 pi radius times height with respect to y. So I'll take the 2 pi in the front and distribute the y, the 4y minus y cubed dy. We'll take the antiderivative. 4y squared over 2 minus y to the 4 over 4. So the antiderivative at 2 will be 16 over 2 minus 16 over 4 minus 0. So 8 minus 4 is 4 times 2 pi is 8 pi units cubed. Here again, the graph is given just for reference. You can see it sort of looks like a dome, and it's not hollow inside, it's completely solid. In the next example, find the volume of the solid obtained by revolving the region enclosed by the x-axis and the parabola 3x minus x squared around the line x is equal to minus 1. So the x-axis is the line y is equal to 0. We can find the points of intersection. 3x minus x squared is equal to 0, so we can factor. So we have the points 0, 0, and 3, 0. We see it's a negative parabola, so the vertex is in between 0 and 3 and above the x-axis. So again, we're using shells, and we're revolving around a vertical axis. X is equal to minus 1. So the representative rectangle will be parallel to the vertical line. It has small width dx, so then we know that our integral will be with respect to x. So the height of the shell will be the height of the rectangle, which is 3x minus x squared, and the radius of the shell will be the distance from the rectangle to the axis of rotation. So either you can look at your sketch and see that the radius will be x plus 1, or you can find the distance of the right minus the left. So here I'll write x minus 1. So the radius of the shell is x plus 1. We also see the limits of integration will be from 0 to 3. So the volume will be the integral from 0 to 3, 2 pi, radius times height. So we can FOIL out the terms. We have 3x squared plus 3x minus x cubed minus x squared with respect to x. So here I will just add the like terms. So evaluate the upper limit minus the lower limit. Put them over common denominator 4. We have 2 pi times 45 over 4. So just check if the volume is 45 pi over 2 units cubed. And again, the graph is just given for reference. The shape resembles maybe a bundt cake or half a bagel.
The following problem is from Richard Shoemaker, who taught physics and astrophysics at Dawson College. It is about the formula for the gravitational potential energy of a uniform density sphere. For a uniform density sphere, the gravitational potential energy U is given by this formula, negative 3 over 5 gm squared over r, where capital R is the radius, and capital M is the mass, and g is the gravitational constant in SI units. We will derive this formula using a shell method, but instead of using cylindrical shells, we will build up the potential energy using concentric spherical shells. We know that the gravitational potential energy U of any configuration of masses equals the work needed to assemble the configuration starting from infinite separation. For 2 point masses m1 and m2, separated by a distance r, the gravitational potential energy U is negative g m1 m2 divided by r. Note that U is negative, which means you don't need to do work to assemble the configuration, but rather the masses fall together spontaneously, releasing energy. We also know that so long as you're outside a spherically symmetric mass distribution, it has the same gravitational potential as a point mass located at its center. We want to assemble a sphere of mass capital M and radius capital R having a uniform density ρ. Suppose we have already assembled a smaller sphere of mass little m and radius little r. Bring in an additional bit of mass dm and shape it into a thin spherical shell of radius r and thickness dr surrounding the small spherical mass that was already there. The volume of a sphere is 4 pi r cubed over 3, and since mass is density times volume, the mass little m of the small sphere is given by ρ times 4 pi r cubed over 3. The mass of the thin spherical shell, which is the differential of m, dm, which will be the derivative of m with respect to r, times dr. Here ρ 4 pi over 3 is a constant, and the derivative of r cubed is 3r squared. So here we can cancel 3 and 3. So dm is ρ 4 pi r squared dr. Here we can see the volume of each shell is the surface area of the shell, 4 pi r squared, times the small thickness dr. Each shell that is brought in from infinity to a radius r surrounding the spherical mass will produce a small change in the potential energy. This small change, du, will be equal to negative gm over r times dm. Next, we can plug in the expressions for m and dm into our formula for du. So du will be negative g over r m times dm. To simplify, instead of dividing by r, we'll multiply by 1 over r. And the top will simplify to rho squared 16 pi squared times r to the 5. So for du, we have negative g rho squared 16 pi squared r to the 5 dr over 3 times 1 over r. So the r and r will cancel, and we are left with r to the 4 in the numerator. Next, we can integrate du for u. We can integrate over all the radii. So negative g rho squared 16 pi squared over 3 is just a constant. And then we have the integral of r to the 4 with respect to r. And the integral is going from 0 to capital R. So the integral of r to the 4 is r to the 5 over 5, which we evaluate at capital R minus at 0. So the potential energy is given by this expression. Since the mass capital M is equal to rho 4 pi capital R cubed over 3, we can isolate for the density rho in that equation. It will be 3m over 4 pi r cubed. So we can replace rho squared with 3m over 4 pi r cubed all squared. Next, we can square each term in the bracket. So rho squared becomes 9m squared over 16 pi squared r to the 6. We can cancel 16 pi squared in the top and bottom. We can also cancel r to the 5 in the top and bottom. So we are left with negative g m squared over r times 9 over 15. 9 over 15 has a common factor of 3, so it will reduce to 3 over 5. So for a uniform density sphere, the gravitational potential energy U is given by negative 3 over 5 gm squared over r. This formula was used in a previous related rates video about the gravitational contraction of the Sun.